Subsea Digital Radiography Testing, SDRT, using ROV for pipeline inspection, advanced underwater inspection for pipeline safety and integrity. Subsea Digital Radiography Testing, SDRT, Overview, Objectives of Subsea Pipeline SDRT Inspection, Applicable Standards and Codes, SDRT System Architecture, Onshore Site Inspection Test, SIT, Purpose and Scope, SIT Equipment and Tooling, SIT Execution and Image Qualification, Offshore Mobilization and System Integration, ROV Deployment and Pipeline Identification, Pipeline Cleaning and Preparation, Subsea SDRT System Positioning, Alignment and Radiation Safety Checks, Digital Radiographic Image Acquisition, Inspection Coverage and Multiple Shot Strategy, Data Logging and Traceability, Post-Inspection Activities and Demobilization, Image Interpretation and Reporting, Technical Challenges and Risk Considerations, Conclusion and Engineering Value. Subsea Digital Radiography Testing, SDRT, is an advanced non-destructive testing method used to evaluate the internal integrity of subsea pipelines and welds without physical sectioning or interruption to service. Unlike conventional film radiography, SDRT employs digital detectors that allow real-time image acquisition, rapid assessment, and improved image quality control. When combined with a remotely operated vehicle, ROV, SDRT becomes a powerful inspection solution capable of operating in deep water, high current, and restricted access environments where diver intervention is not feasible. The ROV acts as a mobile and stable platform to transport, position, and manipulate the radiography equipment with high precision around the pipeline circumference. This approach significantly reduces inspection risk while increasing inspection coverage and data reliability. SDRT using ROVs is particularly valuable during construction, pre-commissioning, and in-service inspection phases, where weld quality and defect detection are critical to long-term asset integrity. The digital nature of SDRT enables immediate verification of image quality, compliance with inspection standards, and traceable digital archiving of results. This slide introduces the fundamental concept of SDRT, its integration with ROV systems, and its role within modern subsea integrity management strategies. Understanding this overview is essential before examining the detailed engineering workflow, equipment configuration, and operational steps that follow in subsequent sections. The primary objective of subsea digital radiography testing using ROV is to verify the structural integrity of subsea pipeline girth welds and detect internal defects that could compromise safety, reliability, or service life. These defects may include lack of fusion, lack of penetration, porosity, slag inclusions, and cracks that are not visible through external inspection methods. By identifying such discontinuities early, SDRT supports informed engineering decisions regarding acceptance, repair, or monitoring of pipeline assets. Another key objective is to ensure compliance with applicable industry standards and project specifications, such as DNV, ISO, or ASME requirements, which mandate radiographic verification of critical welds. SDRT also aims to minimize operational risk by eliminating the need for diver-based radiography and reducing offshore exposure to radiation through controlled, remotely executed operations. From an asset management perspective, the inspection data generated contributes to long-term integrity databases, enabling trend analysis, remaining life assessment, and regulatory reporting. Additionally, SDRT provides high-resolution digital records that can be reviewed by multiple stakeholders, audited, and reanalyzed if required. Overall, the objectives of SDRT extend beyond defect detection. They encompass safety assurance, regulatory compliance, cost optimization, and the enhancement of lifecycle integrity management for subsea pipeline systems. Subsea digital radiography testing activities are governed by internationally recognized standards and codes to ensure consistency, reliability, and safety. Key standards commonly applied include DNV-STNDT, which provides requirements for non-destructive testing of offshore structures, and ISO 17636, which specifies techniques for radiographic testing of welds using digital detectors. ASME Boiler and Pressure Vessel Code Section 5 is also frequently referenced for radiographic examination principles, acceptance criteria, and qualification of procedures and personnel. These standards define critical parameters such as image quality indicator, IQI, selection, sensitivity requirements, geometric unsharpness limits, and exposure conditions. Compliance with these codes ensures that SDRT results are technically valid and acceptable to regulatory bodies, classification societies, and project stakeholders. In addition to inspection standards, radiation safety regulations and offshore safety management systems must be adhered to, covering source handling, exclusion zones, emergency procedures, and personnel competence. During both site inspection test, SIT, and offshore execution, procedures must be qualified and approved in accordance with these standards. This slide emphasizes the importance of standards as the foundation for engineering credibility, inspection repeatability, and safe execution of SDRT operations using ROV systems. The SDRT system architecture integrates multiple subsystems into a cohesive inspection solution. At its core is the subsea-rated X-ray generator, typically operating in the 150 to 300 kV range, designed to penetrate pipeline wall thickness while withstanding hydrostatic pressure. Opposite the source is a digital flat panel detector housed in a pressure-compensated enclosure, capable of high-resolution image capture. These components are mechanically integrated into an ROV deployable skid or tool frame, allowing stable positioning and alignment. The ROV provides mobility, power distribution, and precise manipulation through its thrusters, manipulators, cameras, and navigation sensors. Data and control signals are transmitted via the ROV umbilical, often using fiber optic communication, to a topside control container where operators monitor live video and radiographic images. Image acquisition and processing software enables real-time assessment, parameter adjustment, and data storage. Supporting systems include power supplies, collimators, alignment tools, and radiation safety interlocks. This architecture ensures that SDRT can be executed efficiently and safely in subsea environments while delivering high-quality, traceable inspection data. The Site Inspection Test, SIT, conducted in an onshore workshop is a critical qualification phase prior to offshore deployment of the SDRT system. The primary purpose of a SIT is to verify that the complete inspection system, including SDRT equipment, ROV interfaces, software, and procedures, functions as intended under controlled conditions. During SIT, a pipeline test specimen representative of the actual offshore pipeline, matching diameter, wall thickness, and weld configuration, is used to simulate real inspection scenarios. Artificial or known defects are introduced to validate detection capability and image quality. The scope of SIT includes mechanical integration checks, functional testing of the X-ray source and detector, alignment verification, optimization of exposure parameters, and demonstration of image quality indicator sensitivity. SIT also allows inspection personnel and ROV pilots to familiarize themselves with handling, positioning, and coordination requirements. Successful completion of SIT results in procedure qualification, parameter finalization, and stakeholder confidence that the system is ready for offshore execution. This step significantly reduces technical and operational risks during actual subsea inspection campaigns. A comprehensive set of equipment and tools is required to conduct the site inspection test effectively. This includes a pipeline test spool with representative welds, calibrated dimensional measurement tools, and artificial defect inserts. The SDRT equipment comprises the subsea-rated X-ray generator, digital flat panel detector, power supply unit, collimators, and calibration blocks such as step wedges. Image quality indicators, including wire or duplex IQIs, are used to verify sensitivity. An ROV or ROV simulated handling system is employed to replicate subsea positioning and manipulation, complete with manipulators, cameras, and lighting. Data acquisition hardware, inspection workstations, and licensed software are necessary for image capture and analysis. Alignment jigs, clamps, and mounting frames ensure repeatable geometry. Radiation safety equipment, including warning systems and interlocks, is also part of the SIT setup. Collectively, this tooling validates not only inspection capability but also operational practicality and safety readiness. During SIT execution, the SDRT system is operated end-to-end to replicate offshore inspection conditions as closely as possible. The ROV or handling system positions the X-ray source and detector on opposite sides of the test weld, ensuring correct source-to-detector distance and alignment. Exposure parameters such as voltage, current, and exposure time are adjusted to achieve optimal image quality. Digital radiographs are acquired and immediately reviewed to assess contrast, sharpness, and IQI visibility. Known defects embedded in the test specimen are evaluated to confirm detectability and sizing capability. Any issues related to handling, alignment, software performance, or image quality are identified and corrected. The qualification process confirms that the procedure meets acceptance criteria defined by applicable standards. Successful SIT execution provides documented evidence that the SDRT system is technically capable and operationally ready for offshore deployment. Following SIT approval, the SDRT system is mobilized offshore as part of the overall ROV spread. Mobilization involves transporting the SDRT skid, X-ray source, detector, control electronics, and spares to the inspection vessel. Onboard integration includes mechanical mounting of the SDRT skid to the ROV, electrical and data connections through the umbilical, and configuration of topside control and imaging systems. Functional checks are performed to verify communication, power stability, and live image transmission. Radiation safety systems and emergency shutdown features are tested in accordance with offshore safety procedures. This phase ensures that the system remains fully functional after transportation and that vessel-specific interfaces are correctly configured. Proper offshore integration is essential to avoid delays and ensure safe, efficient inspection operations once subsea deployment begins. The offshore inspection sequence begins with the deployment of the ROV using a launch and recovery system, LARS. Once in the water, the ROV navigates to the seabed and transits to the pipeline location using a combination of navigation sensors such as Doppler velocity log, inertial navigation systems, and sonar. Visual cameras and imaging sonar are used to positively identify the pipeline and specific weld locations based on drawings, markers, or field joints. Accurate identification is critical to ensure correct weld inspection and data traceability. Environmental conditions such as currents and visibility are assessed, and the ROV is positioned to provide a stable working platform. This step establishes the operational context for subsequent cleaning, positioning, and radiographic inspection activities. Before SDRT can be performed, the pipeline weld area must be adequately cleaned to remove marine growth, debris, and coatings that could interfere with positioning or image quality. The ROV uses dedicated cleaning tools such as rotating brushes or high-pressure water jetting systems to expose the weld crown and adjacent pipe surface. Cleaning ensures proper seating of clamps or alignment frames and minimizes geometric uncertainties. Visual inspection is conducted to confirm cleanliness and accessibility. Proper preparation is essential for achieving consistent source-to-detector geometry and reducing the risk of image artifacts. This step highlights the importance of surface condition even for volumetric inspection methods like radiography. With the pipeline prepared, the ROV positions the SDRT system around the weld. The X-ray source is placed on one side of the pipe while the digital detector is positioned directly opposite, using manipulators, clamps, or dedicated alignment frames. Correct positioning ensures adequate coverage of the weld volume and compliance with geometric requirements defined during SIT. The ROV's cameras and laser alignment tools assist in confirming centering and orientation. Stable positioning is critical, particularly in areas with seabed unevenness or current-induced movement. This step demonstrates the importance of mechanical design and ROV handling capability in achieving reliable subsea radiographic inspection. Prior to image acquisition, final alignment and radiation safety checks are conducted. Alignment verification ensures that the X-ray beam is correctly oriented through the weld and onto the detector, maintaining the qualified source-to-detector distance. Radiation safety protocols are confirmed, including activation of exclusion zones, verification of interlocks, and readiness of emergency shutdown systems. Communication between the ROV team, inspection personnel, and vessel management is maintained to ensure no conflicting activities occur. These checks are essential to protect personnel, equipment, and the integrity of inspection data. This step reinforces the disciplined approach required for safe offshore radiographic operations. During image acquisition, the X-ray source is energized and digital radiographs are captured by the detector. Images are transmitted in real time to the topside inspection workstation, allowing immediate assessment of quality and coverage. Exposure parameters may be fine-tuned based on initial results, within the qualified range established during SIT. The ability to review images instantly is a key advantage of SDRT, reducing the need for repeat exposures and minimizing offshore time. Multiple exposures may be taken to cover the full circumference or thickness of the weld. This step represents the core inspection activity where volumetric weld integrity is directly evaluated. To ensure complete weld coverage, a multiple shot or rotational inspection strategy may be employed. Depending on pipe diameter and wall thickness, several exposures at different angular positions may be required to inspect the entire weld volume. The ROV repositions the SDRT system incrementally, maintaining consistent alignment and geometry. Each shot is logged with corresponding weld identification and positional information. This systematic approach ensures no inspection gaps and supports defensible inspection records. Coverage strategy is defined during engineering planning and validated during SIT, then executed offshore with precision. Accurate data logging and traceability are essential components of professional SDRT operations. For each exposure, inspection parameters such as voltage, current, exposure time, weld ID, pipeline KP, and ROV position are recorded. Digital images are stored in secure databases with appropriate metadata to enable future retrieval and audit. Video recordings of ROV operations may also be archived to support inspection context. This systematic data management ensures compliance with quality requirements and supports long-term asset integrity programs. Traceability enhances confidence in inspection results and facilitates regulatory or third-party review. After completion of inspection activities, the SDRT system is safely powered down and secured. The ROV is recovered to the vessel using the LARS, and the X-ray source is returned to its shielded storage container. Post-inspection checks are conducted to ensure equipment integrity. Demobilization planning minimizes offshore time and ensures safe handling of radiation sources. This phase marks the transition from field execution to detailed analysis and reporting, emphasizing operational discipline and safety closure. Detailed image interpretation is carried out by qualified radiographic inspectors using calibrated workstations and software tools. Images are evaluated against acceptance criteria defined by applicable standards and project specifications. Detected indications are characterized, sized, and classified, and their acceptability is determined. The final inspection report includes a summary of inspection scope, methods, parameters, results, and conclusions. Digital images are appended or referenced as part of the deliverable package. High-quality reporting ensures that inspection findings can be clearly understood and acted upon by engineering and asset management teams. SDRT using ROVs presents several technical and operational challenges that must be managed through engineering design and planning. Water attenuation of X-rays requires higher energy levels and careful parameter optimization. ROV stability can be affected by currents and seabed conditions, impacting alignment. Data bandwidth limitations may influence real-time image transmission quality. Radiation safety remains a critical consideration, requiring robust procedures and controls. Understanding these risks allows engineers to implement mitigation measures such as stable mounting frames, redundancy, and conservative safety margins. This slide emphasizes proactive risk management as a hallmark of professional offshore inspection operations. Subsea Digital Radiography Testing using ROVs represents a mature and reliable inspection solution for subsea pipelines. By combining advanced digital imaging technology with remotely operated deployment, SDRT delivers high-quality volumetric inspection while minimizing risk to personnel. The structured workflow from onshore SIT qualification through offshore execution ensures technical robustness, safety, and compliance with international standards. For engineers and asset owners, SDRT provides valuable data to support integrity management, regulatory compliance, and informed decision-making throughout the pipeline lifecycle. This conclusion reinforces the engineering value of SDRT as an essential tool in modern offshore inspection strategies.